Liquid holdup. What happens in liquid holdup is a gas and oil or any liquid, oil or water is moving up together. Now, because oil or liquid density is higher, so high density fluid try to slip down, where gas will try to move up because lightweight. Now, if you see the terminal velocity, if gas velocity is not very high, then small liquid particle slowly it will be sliding down, sliding down, slide down. What will happen? I have wellbore, okay, P reservoir, PWF, right, and I have perforations, tubing is here. Now, reservoir pressure say 100 bar, okay. At 100 bar, you are getting gas moving up, okay. Now, if your gas velocity goes down because reservoir pressure 100 bar to 50 bar it reduces, what will happen? Though initially you created mist flow, so whatever liquid was coming, this is gas well. Gas well, this is for gas well basically. So, gas moving out very high speed, so you create mist flow, so that liquid whatever you are producing it will go up with the gas. Now, because of reservoir pressure depletion, let's say it become 100 bar to 50 bar, okay. So, gas velocity went down. Because of gas velocity went down, so the whatever liquid particle was trying to move up, okay, it will try to move down because terminal velocity may be higher. So, terminal velocity higher means it is moving down, although gas is trying to pushing it up because of buoyancy and drag force, but its own weight it will try to move down. When it is trying to moving down, what will happen? Slowly one particle will be blocking, taking some space, 2 particle, 3 particle, 4 particle, 5 particle, 5, then finally it will be held up here, okay. When it is held up, so initially what was the column pressure, okay. So, because you have gas, column pressure almost very low. Now, you got certain amount of liquid, right, pressure. So, this column pressure become P. So, now what reservoir pressure 50 bar, this column pressure, if column pressure become almost 50 bar, this liquid or water and oil mixture column pressure H rho G almost 50 bar, then what will happen? This reservoir fluid will not try to enter into the wellbore because pressure difference almost same, pressure difference almost 0. If we can remove this fluid liquid column whatever build up in the tubing by certain means, maybe artificial lifting system or other system, then again liquid will enter, liquid and gas will enter and you will get production. So, if you are not removing that liquid, your production rate will be going down, 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 finally it will be stopping because the column pressure will be almost equal to reservoir pressure. So, in that case production will be very low or almost negligible. So, in that case you need an artificial lifting system. So, if liquid is held up at the bottom, your production is going down. So, you have to understand what is liquid held up, how to remove it, okay. So, normally artificial lifting system, now a few barrels per day, a barrel of oil or water will be there per day. So, in that case maybe you can use sucker rod pump or some other sort of artificial lift, we will discuss later. But we have to remove this gas, liquid with gas, okay. So, we have to know what is the physical property of this one and what the sort of formula will be there for this one. So, liquid held up formula is there, HL equals VL divided by V, okay. So, here YL is the liquid held up or VHL is the liquid held up, and UL or VL is the volume of liquid phase, volume of liquid phase, and volume will be cubic feet, and V is the piping area, volume of piping. So, it is also again FTQ. So, it is to ratio. So, it is actually unitless, it is fraction. Now, other two term will come here, one will be slip, and liquid held up. So, slip. Slip means liquid held up is happening because gas is moving up and liquid is not following the same velocity. So, it is slipping down actually. So, this is called slip. So, slip formula will be this. First you have to understand the superficial velocity. VSL, superficial velocity equals QL by AF. QL is the liquid flow rate and AF is the flow area for one phase. So, QL how much liquid is flowing and how much area it is taking. So, total flow area. So, this ratio is called slip velocity for liquid. So, similarly you can define slip velocity of gas QG by AF. Now, gas void fraction equals Vg by V, and liquid void fraction was VL or UL by V, and total gas void fraction they are writing as alpha G. Okay, so alpha G plus HL equals 1 because total area, total fraction. So, total fraction must be 1. Now, slip velocity, this is superficial velocity, these are superficial velocity. Okay, super velocity for gas, and this one superficial velocity for liquid. Superficial velocity for liquid. So, slip equals actual velocity of gas minus liquid, Ug minus UL. Now, we will try to solve one problem based on the superficial velocity and slip velocity, so that you will understand more. So, this is GATE question, GATE exam question 2022. So, question was like this: in a horizontal pipe, in a horizontal circular pipe, circular liquid and gas are flowing. Same superficial velocity and has same superficial velocity. Okay. However, the average velocity of gas, is greater than the average velocity of liquid. If the slip velocity is equal to the superficial velocity, if the slip velocity is equal to superficial velocity, each of the phases the fractional liquid holdup Now we will solve one multiphase problem. This problem came in GATE exam in 2022. The problem statement is like this: in a horizontal circular pipe, liquid and gas flowing, and same superficial velocity they have, and the average velocity of gas is greater than the average velocity of liquid. If the slip velocity equals superficial velocity of each of the phases of the fractional liquid holdup is, so we have to find out how much fractional liquid holdup will be there. So to solve this problem, we have to first V slip slip velocity equals V gas minus V liquid. Okay, so this is actual gas velocity, actual liquid velocity, actual liquid velocity. Okay, and V gas equals VSG, superficial velocity, divided by the liquid gas holdup fraction, and V liquid 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 equals VSL by HL. Now V slip equals VSG by HG minus VSL by HL. HG equals 1 minus HL. This total should be 1. Okay. Now V slip equals VSG by HG minus VSL by this one. So I can replace HG by 1 minus HL. VSG by 1 minus HL minus VSIP SLIP divided by HL. Sorry, this is VSL, not SLIP. This is VSL. So now VSG here. Okay, VSG given there. VS slip equals VSG equals VSL. This is given. This is given in the problem. So it becomes V slip 1 by 1 minus HL minus 1 by HL. So this gives 1 equals left side equals right side, or V slip left side and right side V slip gone. So 1 equals 1 by 1 minus HL. So this is HL minus 1 minus HL. So this will give HL square minus HL minus 1 equals 0. Okay, equation 1, let's say. Now equation 1 gives, what will give? HL equals minus 1 plus minus root over 1 minus 4 divided by 2. So it will give 1 plus minus root over 5 divided by 2. If plus sign is taken, then HL is 1.615. If minus taken, it HL becomes 0.615, and this 1.615 is impractical. Hence HL is 0.615. This is the solution for the get question. Okay, and guess question they have given range 0.6 to 0.65, so it is coming within that range. So this is the solution of this problem. So in exam I can give similar sort of problem. Maybe I can give some values also in some cases. Now whenever you are solving multiphase flow, there will be two type of solution. One will be homogeneous model, one will be separated model. So homogeneous model a little bit easier, but easier does not mean this is very easy like 2 plus 2 equals 4. There are several correlations. So one correlation is Poettmann and Carpenter correlation. So we'll see what is the correlation. So here the formula is taken from the Guo and Galambor book, Petroleum Production Engineering, 2007. I think 2007 they published. The formula is like this: pressure drop equals rho bar plus K bar divided by rho bar del H 1 by 144. And the values are like this. del P in PSI. Rho bar is average mixture density LB by FTQ. K bar one parameter we will discuss later, and del H the depth increment in feet, and 144 is one constant. And K bar formula, if you want to find, then you have to go to friction factor, then you have to go to flow rate, oil flow rate, STB per day, and F2F is fanning friction factor, fanning friction factor, and M is the total mass associated with total mass associated with 1 STB of oil, 1 STB of oil, and D is the tubing diameter. This is also in feet, and rho bar is calculated as rho 1 plus rho 2 divided by 2, and rho 1 rho 2 are like this. Mixture density at tubing segment, top tubing segment, mixture density at top tubing segment. LB divided by Q, and rho 2 bottom, again same unit, LB FTQ, and rho is M by VM, and M is given as here, and M is gamma O, is oil specific gravity, SP gravity of oil, that is 1 for fresh water, 1 for water. This is GOR, you already know, this is gas oil ratio, rho air density, and gamma G gas gravity, gas specific gravity. And where VM already there in rho equation, so VM will be coming BO, formation volume factor, WR is the producing water oil ratio, BW is formation volume factor of water, gas oil ratio, RAC solution gas oil ratio, P is the in situ pressure, T is temperature, Rankine, Z is compressibility factor. Compressibility LI, BILITY factor. Rho air density LBM per feet. So rho air LBM cubic feet, and gamma G gas specific gravity 1 for air, and VM volume mixture associated 1 STB of oil, BO formation volume factor. We know already, the unit is RB by STB, reservoir barrel divided by stock tank barrel, and BW formation volume factor of water. So normally it will be 1, rho in situ pressure, P is in situ pressure, unit is PSI. Z composite factor anyway for specific P and T, and F term we have seen in K formula. Here is F, fanning friction factor. Fanning friction factor can be found from 10 power 1.44, 2.5 log D rho V. This formula was developed by Galamba, the author of the book, and just to avoid this chart, Poettmann and Carpenter, they have given one chart for finding F2F, but they have developed this formula. So D is tubing diameter, V is the velocity, rho is the density. this is Reynolds number. If you write, that is top term is d rho v. Okay, so that d rho v formula will be like this: m is the total mass, and q is the oil flow rate, d is the tubing diameter. So in that way you calculate pressure drop for homogeneous flow using Poettmann and Carpenter equation. So there will be many other equations also, but because this is not our multi-phase course, this is only for artificial lifting systems, just to give basic idea. We need to know the formula associated with basic calculation when you are considering homogeneous flow. Homogeneous flow means we are assuming particles are very small and mixed homogeneously. But if particles are like slug flow, plug flow, or other type of flow, that particle will not be mixing homogeneously. So in that case, you cannot use. Although this is very much approximated formula, but still people are using, because this is very simple to use for oil field fluid calculations. Again, we said we have homogeneous flow model, we have separated flow model. In separate flow model, it will be giving much more accurate result, but this is very much complex because manual calculation will be very much difficult. But we should know how to develop or how to calculate for separate flow model. Separate flow model basic equation is that pressure gradient del P by del Z equals G by Gc rho bar to FF rho Fu EM square Gc by D, and this velocity term UM square del. Now if you are using US field unit, then you have to put this 144 term, all these terms, extra terms will come for field unit. And for rho again you are calculating YL PL Y minus YL GL. So rho bar in situ average density, in situ rho bar in situ average density, in situ average density, m total mass flow rate, MT total mass flow rate, and unit is lbm divided by d, and rho is lbm per ftq, d means day. So one term is the um is the mixture velocity, mixture velocity unit will be feet per second. Rho bar, it will come as YLPL. PL is the liquid density, PL liquid density, and the unit is lbm per feet cube, and rho g gas density, lbm again feet. USL, the terms are used next equation, USL and USG, those are superficial velocity for liquid, and this is for gas, superficial velocity for gas. Now using all this formula, you have to calculate liquid velocity number. This is called liquid velocity number, and this is gas velocity number. This is gas velocity number. This is pipe diameter number. This is liquid. Using these numbers, Hagedorn and Brown, they develop charts like CNL. This chart is like this, NL, this is log plot. Another is Holdup factor, and this is NLV P 0.1 C LN L divided by N GV 0.575 P A 0.1 ND. So this sort of big formula they develop, and they develop some curve. So from the curve actually you can calculate pressure drop. Okay, this is liquid holdup. Liquid holdup. This is a liquid viscosity number. Now we have seen multiphase flow for liquid and gas. We have seen liquid flow. We have seen single phase liquid flow. Now this is for single phase gas flow. Single phase gas flow is having equation like this: pressure del P divided by rho G by Gc d del dz Fm v square dl 2gc by dt. So terms dz equals cos theta dl. L is piping length, cos theta is the angle of the pipe from vertical. Rho density will be 29 gamma g, P in situ pressure, Z RT. R universal gas constant, RT, Z is compressive factor, T is temperature, and nu equals 4 Q Z P T pi d T square T P. So these terms, if you can find or if you can give, then you can calculate actually single phase gas flow. So in the whole lecture we have seen that there are two type of thing. One is vertical pipe, one is horizontal pipe. In vertical pipe, flow physics will be different, horizontal pipe flow physics will be different. Now if we have different types of artificial lift, then the artificial lift will be behaving differently if we have more gas into wellbore, or less liquid, or multiphase you are creating, or emulsion you are creating. So if you are getting more emulsion, maybe you will get more problem because of viscosity, and your pumping electrical power for pumping will be more. But if you have more gas, the gas maybe it will be giving failure to your ESP system or sucker pumping system or other pumping system. So whenever we will discuss about different types of artificial lifting system, so that time we will discuss in details how this gas will be affecting your pumping system and how it will affect your whole economy of the whole production system. So thank you very much.